Okay. So, wrapping up Chapter 6, Physical Transformations of Pure Substances. The Ehrenfest Classification of Phase Transitions. Okay. And there's two of them that they found in nature, two different types of phase transitions. And they talk about how the chemical potential changing with temperature is either continuous or discontinuous. And that's how they kind of specify the difference between the two. If I was going to plot, what does discontinuous look like? All right, it's going up, cranking up the temperature, it hits the phase transition. I'm plotting molar Gibbs energy, or chemical potential versus temperature for this pure substance. What does discontinuous look like? It could be a step or a hole, right? Or it could just be an abrupt change in slope. That would work too, right? So you could have it something like this. But in nature, what happens is more like this, right? It's just an abrupt change in slope, right? You know, right? It's just an abrupt change in slope is discontinuous. Different compounds are going to give you different looking things, but what is the heat capacity? Sandy, what is the heat capacity? Well, what is heat capacity first? When I give my answer to stuff like that, I just go by the units. So think about what the units are. That might be a guide. Joules per Kelvin or joules per Celsius, right? You can have joules per Celsius mole. That's not heat capacity. Technically, that's what heat? Specific heat. So the word specific is thrown in there when it's per amount. But just heat capacity, it's just joules per degree Celsius. How does that help you define what it is, Emily? It's because joules is energy or heat, right? The amount of energy it takes to raise this thing 1 degree Celsius or 1 degree Kelvin, whatever your units are. So that's how I use the units to answer the question. Okay, what is the heat capacity, Anna, of water when it's boiling? Hey, let's back up. What is the heat capacity of water when it's not boiling? Is it a specific number? Something that you could Google and look up? Yeah, right, why not? Okay. Juan, what's the heat capacity of water when it's boiling? Now, if it's a number, right, you've probably seen these. If I have temperature, time, okay, let's say at 1 atmosphere, the freezing and the boiling point of water. The freezing point this is going to be a long answer to answer this question that I asked Juan. What's the heat capacity at the boiling point? But you're getting there. Okay, what's the freezing point of water? Let's stick to Celsius, so much easier. Boiling point, 100. Okay, we're going to start out super cold, I don't know, -10. And we're going to go way up to 110. Okay, we're going to start here. Just let the stuff sit there. Monitor the temperature over time. You're going to start out by drawing this thing how, Amberly? Yeah, kind of incline, go up a little incline there. Is it going to be a straight line or is it going to be a curvy line? you're saying two different things. Either one, versus...
I remember this from physics, and we would always do straight lines.
You do straight line if what? Is not changing over that temperature range. What did I ask Sandy about? The heat capacity. If that heat capacity is not changing over temperature, it's going to be a straight line. I bet you if you made that super, super cold and it got into that ice 2 or those different, I bet you the heat capacity is going to be changing over temperature. Then it could be curvy, straight, or it could be straight, right? And who knows? It'd be funky looking. But usually you just draw a straight line because you're saying the heat capacity is constant over time. Constant over temperature, sorry. And then you hit 0. And then what happens? Flat. Now it stays flat. If you're sitting there staring at that thing, Kathleen, right? This thing is just sitting there watching like ice melted. It used to be very boring, right? But you're watching it. So then you start getting a puddle, right? And you have that ice cube now floating in there. Are you still in the flat region? Until it's all liquid. Exactly. It's going to be on that flat part until it's all liquid. I guess you got to keep the thing stirring up, otherwise one part's going to get warmer than the other. But yeah, it's going to stay flat until it's all liquid. And then curvy line or straight line? It's the same question again, right? Does the heat capacity of water change over temperature? I don't know. If you say straight, then you're saying it doesn't, right? So, fine. Where's 100? 100's probably around here somewhere. Then what? So are we heating this thing up or letting it cool down? We're heating it up. So does that mean it's sucking up energy? But it's a flat line. Same as down here with melting. It's a flat line. It's sucking up heat. You're going to, with a top one at 100 degrees, it's going to stay flat until well, we're keeping the pressure the constant the whole time. Otherwise, this whole thing, you get into phase diagrams and it gets really ugly. We're going to keep the pressure at 1 atmosphere. When does it start turning flat? When it starts what? Well, we're heating it. So a better word than evaporating might be boiling, right? So it starts turning flat when it starts boiling. Stays flat until, I like Kathleen's answer, but it was for a melting, but stays flat until all the what's gone? All the liquid, right? Okay. So where's all that energy going? Surroundings. Think about it. What are we doing? Yeah. What's going on here? What are we doing?
That last plateau that you have?
Yeah, that plateau here. What are we doing? You got this thing, and it's sitting there boiling, right? Yeah, it looks like on the phase changes, ice to liquid or liquid to gas, you get the what in these plots? The plateaus. So where's the energy going? Yeah, because we're going up the energy ladder, right? So liquid to solid. Or sorry, solid to liquid. Or liquid to gas. Good. Okay. Here's the question now that we asked Juan at the beginning. Alice, what's the heat capacity at these plateaus when this transition's occurring? It's going to be some funky number. Would it be 0? Now, if it's 0, that means you don't have to put any energy in at all, and it's going to happen. But it's sucking up the energy. It has to because we're going from liquid to vapor. So it has to be sucking up energy. So it can't be 0. Now, if it's a positive number, mathematically, this has to have a slope. right? It has to be going, I don't know, whatever your positive number is, right? But it's flat.
If it's flat, it should be 0.
Yeah, the slope is 0, right? But that doesn't answer the question where the energy's going. So that slope, it seemed to make sense. Oh, the slope is the heat capacity on this stuff. It really made sense. But now it doesn't make sense at the phase transition. For a first order phase transition, it doesn't make sense. It's discontinuous. So you have to have a whole new mathematical idea here. It can't be a constant. Well, I'm just thinking the Juan's idea, the number. You Google it. You get 888 joules per degree Celsius or something. Whatever. That would be a slope over time. Because that amount of energy is being sucked up. Heat capacity is, does it matter how much energy you put in? The more energy you kick in, it would just stay flatter for a shorter period of time is all, right? Kick in less energy at that temperature, per unit time, it's going to be flatter longer. Kick in an infinite amount of energy, now I get it instantly. Heat capacity is what? At a phase transition for first order phase transitions. It's infinite. It's infinite. There isn't a number for it. It's not 0 though. It's infinite. Infinitely big. I don't know how you describe infinity. I don't know. But it's a huge, 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 huge number that's immeasurable. It'll suck up whatever energy you give it. It's infinite. Heat capacity is infinite. And it kind of makes sense, right? Because you can boil water and it doesn't matter how much energy you kick in there. It's just all that energy, it's still boiling, and all that energy, does the water change temperature? It can't get any hotter than that. That's the phase diagram. Because things boil when the external pressure equals the vapor pressure. The vapor pressure. So that's boiling. And all the energy is going into turning into the vapor. Okay. Now, since that's the case, that's why you have to be super, super careful boiling anything, especially water. Because all that steam, now you're in a gas. That stuff can grab all that heat and just burn the heck out of you, right? You can stick your hand in the boiling water, hot, fine, but it's not near as bad as steam. Have you ever noticed that when you're cooking? You put your steam just, that's horrible. Anyway.
Yeah.
Okay. So that first order phase transitions, that's the life we're used to. Heat capacity is infinite at a phase transition. We get flat lines at phase transitions. Second order phase transitions, that's where it's kind of odd. It's more like, where's our lambda line? You remember that guy? Here. That's an example of a second order phase transition. Here, heat capacity there actually is a number for it at a phase transition. It's continuous. And funky, weird things like this happen with second order phase transitions. So they're not that common, like lambda lines, where you can't have, the gas can't be, can never be directly converted into a solid, for example. Okay. Yeah, the lambda transition. Okay. Okay.
Is continuous, is it actually a number?
It's actually a number. You can Google it. Yep. You can Google the heat capacity of what's going on at the phase transition of a solid going to a gas. It's that lambda line, an actual line that has a slope. Okay, so that's second order phase transition. It's not really and how would, it's just, one last idea. It's odd. It's hard for me to relate to this because I don't see substances doing this. But for second order, it's just the opposite of first order. First order, you have a heat capacity, right? You're warming it up, getting it to the boiling point or whatever. For second order phase transitions, the heat capacity is infinite in getting it to the transition temperature. And then it becomes a number at the transition temperature, and then when it's completely converted phases, the heat capacity becomes infinite again. It's just the opposite. And I don't know how. I can't. I don't know. I need to see a movie or something of this happening for some reason. I don't know why. You just see little numbers on the dial, but it's odd. Okay. Surface tension. Surface tension. Oh, Juan, you've gone soccer player. Dang soccer ball goes off the soccer field into the lake. Elmendorf, I don't know why they call it a lake, but right? It's sitting there floating. Elmendorf puddle. It's floating. Right? Is that because of surface tension? Yeah? Oh, good question. That's a good point. But the water, if you look closely at that, well, you almost have to go swimming or something, right? Go in there. Is the ball below the surface of the liquid? Yes. So it definitely broke the surface tension. So it's not because of surface tension. It's because density, yeah. Mass over volume. It's less than what number? That dang ball's floating. It's got to be less than...
That's not pure water. I'm just saying.
Well, let's say pretend it is pure water. That was the next step, but 1 gram per mil, right? So get that dang soccer ball, mass it, measure its volume. What's the volume of a sphere?
4/3.
Ooh, good. 4/3.
IR.
Oh, so close. Cubed. All right. Okay. So how do you explain dW equals gamma d sigma in words? W is what? Kathleen, what's W? Work. So it takes work to do what to a liquid? Gamma is surface tension. The real hint here is this d sigma. Now we did this in the concept review. Area. All right? So that means you're changing the surface area of a liquid. You're stretching it. It takes work. It makes sense. Right? It takes work to stretch the surface of a liquid. What's going on in a surface is very different than the bulk. In fact, there's studies out, and we're working with this. You've probably, I think I harped on this before. You take Tylenol. What percent of it do you actually just whiz out into the toilet? Like 90-some%. Okay, all that stuff goes in the sewer, goes to the sewage treatment plant. How much does it get out and clean up the water? None, right? There isn't a sewage treatment plant on the planet that can get rid of this stuff. These are organic compounds in water. It's not built for that. So that stuff, it just keeps, does it evaporate? Does Tylenol in the water evaporate? It's a white solid, right? Right? And does it doesn't evaporate? Is it going to degrade over time? Maybe with UV rays or something, but the point is that it's building up the environment. And in these studies, instead of just taking water samples, instead they just skimmed the liquid because these contaminants have a much higher concentration in the surface than they do in the bulk. So that's one application of this surface tension thing. But anyway, curved surfaces, bubbles. Okay. What's the difference between a bubble, a cavity, and a droplet? Oh, Anna, what's the difference between a bubble, a cavity, and a droplet? Which one is rain? Rain is droplet. right? Solid liquid ball. Bubble and cavity almost seem like the same thing to me, right? Because a bubble has a cavity, right? Like, you wouldn't have a cavity if it wasn't a bubble. I don't think. Well, I guess the cavity could be like, well, whatever. Okay, let's.
It's like concave compass.
Yeah. Is the pressure inside? It's kind of a hint there, Emily, in our next little equation we're talking about. Is the pressure inside or outside of these objects, like a droplet, bigger or smaller? And mathematically, it tells you. Can you see the answer? The pressure is bigger. Pn equals P out plus some number. Pn, the inside of these droplets has a much higher pressure. Okay, now this is where things get interesting, for me at least. I've always been wondering and interested in something called this, the Burgeron process. You'd think something as important as rain they'd have a much better handle on. But you can kind of tell when you see, we think there's an 80% chance this big-ass hurricane, I mean, look at all the energy and the power in that thing, is going to go this way and that way, and it ends up going the opposite direction. How can they not know these things? They don't. Our understanding of our world has a ways to go yet, from my point of view. But here's a good example. This is how they think you get rain. Okay. So you need water. It's called the Burgeron process here. So I want to make, here's some water. Okay. But really what you don't need is the water. You need the water vapor. Amberly, do I have water vapor in here? Well, I have to because I definitely have water liquid. So that means there has to be water vapor. Okay, you can't see it, but everyone believe me? Okay, then you need wind. Okay, now what I'm going to try to do is make a cloud here, according to the Burgeron process. So I'll pump it up. Now if I make a cloud, what does a cloud look like? What? Look like that? Didn't see anything, right? Now Alice might see a little bit of white something going on in there. There might have not really a whole lot. So what we need are hygroscopic nuclei. What we need is, well, we'll tell the whole complicated story later. Hygroscopic nuclei, something for that water vapor to collect onto to make some extremely, extremely, extremely small droplets. Okay. So, guess not that one. I could have used my, oh yeah, okay. So I'm going to drop this in there, and you're going to see a little puff of smoke, maybe. You see a little puff of smoke? Okay. So we should have some hygroscopic nuclei in there. All right. Now, why did I need the wind? Why didn't those little droplets form until I popped the lid off? I needed the pressure to drop. I needed things to get, a little bit colder, right? So that this stuff would condense. Okay. If this is the idea, and it's not the whole story yet, we'll tell you the whole story, but if you actually need hygroscopic nuclei, that means inside every raindrop, every snowflake, everything that falls from the sky, It has to be a hygroscopic nuclei. Is it this? This would be a very smelly world if this is our hygroscopic nuclei. What's the hygroscopic nuclei? Inside every raindrop, every snowflake, this is there. What is it? What's that? No, it's not a gas. It has to be an actual physical piece of crap. Okay, now it's not dirt. It's a good guess. But it'd be, it'd be really dirty and... I'll give you a hint. Our world is covered by 3/4 salt, right? The oceans evaporate. Where the hell does all that salt go? It gets picked up by the wind. Inside every single snowflake, raindrop, everything is an extremely, extremely small crystal of salt. Okay. Now, they've been, just like scientists, they take one thing, build on it, and see if it actually works. Okay, these guys found that. That makes sense. But it needs more. There's, I forget the name of the bacteria, that needs to be on this salt. Otherwise, the water won't collect. So these guys are thinking, let's increase the amount of rain by genetically modifying this bacteria. Seems to me that's the makings of a zombie movie, right? But that's what's going on in the world around us. They're trying to work with this. Now, in this Burgeron process, the whole big picture is... where's my pen? You've got your cloud. All right? This region on the bottom is super saturated. Saturated air. Okay. Now how the heck, what is supersaturated? If I make this sponge saturated, what would it mean? Can't hold any more. What would supersaturated be? It's a physically impossible thing. It's holding more than it physically can. A very stable or unstable situation. Very unstable. But it has to be there. You need a supersaturated region of air. Well, how do you get it? You get it through something like this. Or this, even better. The equation looks better. Vapor pressure of droplets. When do things boil? When vapor pressure equals the external pressure. Let's get this little dang droplet, even though it's cold in that cloud, to boil off. All you need, it sounds weird, but remember, all you need is the what pressure to be the what pressure? Vapor pressure to be, well, whatever it is up there, whatever the pressure is up there. Okay. P star is the vapor pressure of pure water. So you got to look it up in a table and put it in. But look what happens as you make that droplet smaller and smaller and smaller. Now you recognize gamma. Gamma is the surface tension. Vm is molar volume, R gas constant, T temperature. So watch your units when you're playing around with this. But the point is, what's little r? What's little r? We're talking about a droplet. The radius of the droplet. If you make that radius smaller and smaller and smaller, what happens to the pressure inside that droplet? It goes up dramatically, exponentially. The pressure inside that droplet gets so big, it reaches what pressure? External pressure. The thing technically boils. Or I guess evaporates might sound better because boil means you're kind of like adding heat or something, right? But it vaporizes. That's how you're generating this supersaturated region of air. Those droplets need to be extremely small. Okay? So you can get this pure supersaturated region of air. Okay? Spontaneous nucleation centers. Nucleate. What was that in my case? I called it hygroscopic nuclei. That's what the Burgeron guys call it. Yeah, the little tiny smoke particles, right? The real world situation, the spontaneous nucleation centers are salt particles, right? Okay. Okay. So any questions on rain? Capillary action. I'll count up our labs and see if we can honor Dr. Mungia by doing her capillary rise activity that we actually published in the Journal of Chemical Education. And we use this equation and to get surface tensions of liquids. So it doesn't sound all that interesting, right? You stick a capillary tube in a liquid and it rises up. But the fun part, the interesting part of what she did is you get to mess with the laser. And you have to know what R is for that capillary tube. And you can go buy this stuff. You can go buy a capillary tube. Someone measured it, and it's really expensive because you're measuring a little dinky capillary tube. It's expensive. So why not just measure it yourself? Shine a laser through there and create a what pattern? There's the D. Diffraction pattern. And from the diffraction pattern, you can Google it and see what all the different types of diffraction patterns that there are. But the point is certain diffraction patterns are, you get from certain setups. So you can relate what created the diffraction pattern, the size of the little hole. So we do that, and you can get the radius of the capillary tube. Okay, instead of going out and buying this stuff. So to me, that was the fun part of the lab. It's the most frustrating part of the lab, but it would be good for you to go through it, right? Okay, so here's our exercises. In number 9, make sure you change part C to what it states there. Oh, well, the book doesn't say it. Okay. Refer to figure 6.5. What is 6.5? Do we have 6.5 in the outline? We probably don't, huh? Oh, we do. It's that phase diagram of water, yeah.
Phase diagram. It's one with ice too.
Yeah, there it is. Yeah, thank you. There it is. There's figure 6.5. Okay. Describe the changes that would be observed when water vapor at 1 atmosphere and 400 Kelvin. So find where that is on the phase diagram of figure 6.5. And you're going to cool it at constant pressure until you hit 260 Kelvin. Suggest the appearance of the cooling curve. First, I want you to describe the changes. So you do that, and then suggest the appearance of the cooling curve, which is a plot of temperature and time, kind of like what we did at the beginning of the hour. Okay, how would the temperature change over time? So the first part, kind of describe what's going on. The second part, actually draw just a general cooling curve. You can probably put some numbers on there like the 400 Kelvin and the 260 Kelvin where there's changes going on. You're starting at 400 and 1 atmosphere, going all the way down to 260. Are you going below freezing or you stop above freezing? Hopefully you're going to go below it. All right. Took 260 minus 273 to get a negative degree Celsius. And so after you describe your changes, make sure you make your little temperature versus time plot. We're not sure what to do here. So you're starting at 400 Kelvin, so you describe what state? It's got to be 400 Kelvin, what atmosphere? Yeah, but what state though? They want to describe it. Should be a gas, right? Okay. So that means you're cooling a gas. At first, yep. Yeah, you're gonna hit. Now you got to hang out at that boiling point, though. Over time, you're going to hang out at that. Well, boiling point's kind of boiling. I think of as boiling, as the condensation point or the what else? I guess the boiling point's the only word we use for that point, though, right? You're cooling this gas until you hit the temperature at which it condenses. There's no other word besides boiling, is there? Like freezing has freezing and melting, but boiling just has. Yeah. Oh, okay. Okay. Yeah. But just layman's terms trying to explain changes. I don't know how else I just say it condenses all into a liquid. It stays at that temperature, though, until it's all liquid. And then it starts cooling. I think that's what I would be looking at if I was grading this. Is I'd like to see that first you recognize that it's a gas, and then you're cooling that gas, and but then the temperature is dropping, but then it stays flat until all that stuff turns into a liquid. And then the temperature starts dropping again until it hits a solid. Then it stays at that temperature until it all turns into a solid. And then the solid cools. I guess how I would say it. And then you have to draw it in a temperature versus time plot. Yeah, that or these guys are curvy. It's up to you. And you should have the temperatures written over there. All right, so you got 6.8. You comfortable with it? .9, just take a look at it. It seems like that's the same as the last type of homework question. I don't know if we need to. I mean, we can set that one up, but I think. And where you're changing the last part to entropy of what is the entropy of vaporization at the normal boiling point? Oh, I've said that already. Just divide by the temperatures, right? Pretty much all you do is divide by the temperature to get entropy. I'm more interested in this number 11. Make sure that you can do that one. Does 9 make sense? It should. I think it's just, causes clapper on, plug and chug. Just watch your units. How about 11? How about 11? So in number 11, you need to divide, at least in my mind, what by what to get the answer they're looking for. Divide what by what? What's that? Would be on the bottom. Well, that vaporization event, the enthalpy of vaporization, right? Let's just maybe say there's 1 mole. So then, whatever the enthalpy of vaporization of water is, that would go on the bottom. All right, you have to Google it or look it up in the book. All right. Maybe just assume 1 mole or something, so you can put a number down there. Then up on top, in English would be what? The energy used to, So is water vapor? So you're vaporizing water. It's a liquid. When it turns into a vapor, it does. It doesn't have to push the atmosphere out of the way. So that means some of this work, it's going to be PV work. Is it going to be really fast PV work, or is it going to be the reversible PV work? It sounds like it should be reversible because it's a reversible process. But it just happens. It pushes it out of the way. It's fast. It's that, what is it? What's the equation for that? W is minus P external delta V. Remember that? Remember that? So yeah, it sounds to me almost like you'd want to put the reversible in there. I have an urge to too, but it happens too quickly. It's not the process itself. It's just the vapor actually pushing the atmosphere out of the way. So in order to vaporize a liquid, not only you have to put the energy into, the liquid going to a gas, that requires energy, different state. But all that gas then has to push the atmosphere out of the way, whatever pressure. So it takes some work. So all that's part of the enthalpy of vaporization. Well, what percent? Okay, that's the question. So the enthalpy of vaporization, the denominator, the work up on top. So you know what the pressure is, just 1 atmosphere or whatever. Watch your units. How about the change in volume? You're going from what to what? It's vaporizing. You're going from a liquid to a gas. So delta V is V final minus V initial. So it should be V gas minus V liquid. Remember doing this kind of thing? Now they assume what? And rightfully so, I think. Yeah, gas is a huge number. You take a little droplet generator. No, they don't even compare. Volume of liquid is insignificant completely. So it's just V gas. How do you get the volume of the gas? Well, we're assuming what pressure? We're assuming 1 atm. We're assuming how many moles? 1. I'm picking out everything in the ideal gas law. You know what R is? And T is what? Is T 273? It's vaporizing. 273 isn't boiling. 273 is freezing. 373. There you go. And you get the volume of the gas. Okay. And the next, just watch your units. You've done this a lot. And 12, again, watch your units using that vapor pressure of a droplet equation. Okay. What's a nano? 10 to the negative 9. So this is 10 nanometers is like 10 times 10 to the negative 9 meters. So we're about out of time, but come by. I'll be glad to help you out with any of these.